All right. So about questions, if you have any things that you want to clarify, you can ask them right away. But I would recommend the more technical and philosophical questions to be asked towards the end in the Q&A session. You can do that by directly asking the question or typing question in the chat, and we'll get to you in that order. And yeah, with that, please join me in welcoming Professor Patrick Pilarski for our third Tea Time talk of the summer. And he is going to talk to us about time in RL. So take it away, Patrick.
Great. Thanks, folks. Hello, everyone. I was just saying I really like this virtual setup. If you see me looking over here, it's because I have a big monitor with all your smiling faces on it. So I'm looking over there and you're asking a question. I'm looking at you. Otherwise, I'll try to look over here at the camera. And for once, I'm actually going to give a talk on time. No, I've already started late. But time is something that I've been thinking about for many moons, especially for those who've talked to me the last couple of years. It's been something that's been on my mind, especially how animals and machines represent, use time, and form notions of time to aid their decision making. Partly this comes from my work and my team's work on assistive technologies, technologies that interact with people and have to truly understand the context and the flow of the relationship between them and the technology itself. And so time is of essence to those particular kinds of investigations. And looking back at some of the papers we've done over the last decade, many of them have required us to think very hard and to hand engineer notions of time into our decision-making systems so they can interact well with people. So today I'm not going to get into any of the specifics of how we've deployed timekeeping machinery in learning machines. And really, I'd like to focus more on the notion of time itself. I'm going to do so by grounding our talk today in some of the neuroscience literature and then giving you maybe a list of my desirables for how we might wish to pursue agents that take time into account. And to keep in theme with the last couple of talks, perhaps a way to think of this is, in fact, approximating time. Maybe I'm not going to tell you about how agents try to understand and peer into the very bones of the universe to understand the flow of some ephemeral clock, but really how agents might approximate the notion of time. And depending on your viewpoint, maybe this is very, very akin to how agents might approximate memory, or how they might approximate the experiences that they have perceived that have flowed past them already. The main goal for today is to get you really thinking about time. So if we leave by the end of this tea time talk and all you do is think more about how time interacts with the operation of the learning machines that you study, then we've already achieved our goals, but I'm going to hope to do a little more. And to start you thinking about this, I'm going to start with something that maybe you all remember. There was a day in the history of us before we all started working from home when we drove these like metal boxes with wheels on them. And some of you might remember this. We drove around and then we'd stop at these glowing lights, and then you'd have to wait for the lights to change color, and then you'd move your metal box by pushing some pedals. Anyway, so we used to drive these things around called cars. And so right now you can imagine yourself in that situation. You're driving one of these metal boxes around and you have to wait for this red light to turn green. At some point the light's going to turn green and you can go. If you're given no other information about this particular task, if all I'm showing you is this red light, I think it'd be pretty hard for me right now to like query all of you out there and your little GVC boxes and say, okay, tell me when that light's going to turn green. If you nail it on the second, I'll like send a cookie to you by door drop, right? I think you'd all do a pretty bad job of that because you have no information as to when this light might turn. Boom, it just turned. No cookies for anyone. So this is the essence of the problem, is that if we're faced with nothing but this kind of stimulus, it's a really hard decision-making problem. There might be other stimulus in the world. I remember over in other places, you sometimes see a yellow light before the green light, but you might also be in that metal box with wheels driving up to an intersection. You might be stopped there for a while, and you might get an inclination that the light is going to turn green from red because, say, other cars that are going across to you are starting to slow down and stop. You can see this, and you can condition your estimate that the light's going to turn on these other stimulus from the world. Is that everyone's tracking this? If so, I mean, one very natural thing you might then expect is that if I were to say have that sort of red light, some kind of stimulus in the middle, and a green light, and you saw this a couple of times. If I were now to stretch out the length of the duration of experience between, say, the red light and that stimulus in the middle, you might make the very reasonable decision that, oh, okay, it's going to be an equally long amount of time until the light turns green. You might be able to sort of scale your predictions, scale your estimates, scale your decision making as other evidence in your world gives you inclinations that the intervals of time, the intervals of experience in your world have changed. Okay. I'm just going to do this one more time. If you're sitting here staring at nothing but this red light and trying to predict when it's going to turn green, no cookies for anyone, then this is exactly the same case as many of our learning machines face. Some of our old robotic experiments in RLAI, when we had little Roomba create spinning around circles and trying to figure out when they're going to see a water bottle again. When we're looking at prosthetic limbs that are trying to figure out when they should open or close their hand, often especially with impoverished data streams, it's very hard for agents to use their immediate state to make decisions. And so what happens in these settings? And I think we actually, A, don't know, and we, B, do know. This may look a lot to those of you who are familiar with some of the other forms of literature, not just the computing science literature, might recognize that setting I just set up for you is very similar to the one of conditioned stimulus, unconditioned stimulus. You see some kind of event in the world, and you're hoping to, after some interval, be able to forecast the onset of another stimulus. Go back to our good friend Pavlov in 1927, had some very interesting thoughts on what he called trace conditioning. You can go find copies of this particular book, and his thoughts on trace conditioning is that really, when there's an interval with no other stimulus between one stimulus, the conditioned stimulus, and the unconditioned stimulus, that there's still the ability for an agent to be able to start to form predictions, decisions, responses as it starts to approach the onset of this next stimulus, even when arguably nothing else in the world is changing. So what's happening here? There has to be if there's nothing in the world that is changing, there must be something in the agent that is changing that allows it to fill this wasteland, this gap between stimulus, and allow it to make good decisions. Those of you probably many of you already figured out exactly what you might do. You said, oh, well, we can just keep around a time counter. We can have some kind of decaying trace. We could keep around memory or some kind of history that would let us solve this particular problem. How do I forecast the onset of an event after some duration after seeing another stimulus? And what's interesting here is that we could do this, and how we do this forces us to make choices. If we were to use one method, we might have great resolution as the temporal resolution as we start to approach the unconditioned stimulus. That as we start to approach the event we hope to forecast, we might make a choice that allows us to be very accurate around that window of time. We might, as many biological mechanisms do, be very accurate at forecasting the passage of time directly after, say, the conditioned stimulus, but get worse and worse at estimating the passage of time as we get farther away. The choices we make, like we could keep around a history, but at a certain point, the gap between these two events is so vast that it just doesn't make sense for us to store our entire history in between these two events. So that's my way of saying that there are a lot of choices to be made here. And really, we can ask ourselves, well, if there is nothing changing in the world, let's just assume there isn't, then what is it that's changing in the agent? So I'm looking around, everyone seems to be, I see mild skepticism and general smirks. Okay, great, we're on track. So to try to figure out what's actually going on, I'm going to step more directly into some of the neuroscience literature. And I'm going to get back to time by way of space. And in particular, I'm going to think about something that Tolman proposed in a paper in 1948 and some of his other work on cognitive maps. How the brain of an organism, a biological organism, might begin to form maps of the space or perhaps the time that is immersed within. And this relates, you can see I put a bunch of these nice little heat maps because I love heat maps on the top of the slide here. But really, there's a wealth of literature on place cells and grid cells. There was a Nobel Prize in 2014 on these lines of work on studying how the deep brain structures within the human brain and within the animal brain can begin to start to form maps or spatial localizations and represent these as what Tolman would have called cognitive maps, arguably speaking. And very recently, there's been work in the computational literature on how that machines might actually start to build up these similar cognitive maps of space. Maps that let you know where you're in position A or position B, whether I'm in my downstairs guest bedroom giving a talk, or whether I'm outside on the deck. What's really cool, and I think this is it's an interesting paper, and I encourage you to read this if you're interested, is that people have found recently that not only are there sort of place cells and grid cells in the mind, but that in, say, the hippocampus, there are also what's considered as time cells. These are cells that fire, populations of cells that fire a certain interval after a stimulus or within a certain duration over the length of a task. Certain cells will come online. These heat maps I'm showing you right now are from a paper by McDonald et al. And what's neat about that paper is that they do show, if you look at the populations of cells, in this case in the hippocampus of a rat, you can start to see that over the course of a task, and independent of the rat's location or its behavior, there are populations of cells that respond to the duration of time since different stimulus in the rat's environment. What I found really compelling about this too is that it isn't just that, you know, there's a stopwatch in the rat's brain that goes after it smells an odor or a door goes up or a light goes on. It's that some of these populations, not all, but some of these populations do something called retiming. By retiming, I mean that if you were to say, take the duration of a task, say it was a 5-second long task or a 5-minute long task, and you were to study the populations of cells that fired over that task, and then were to change the task to be 10 minutes long instead of 5 minutes long, that some of those cells, some of those populations of cells would in fact stretch out their firing to encompass this new window of time. So this suggests that in the brain structures, there's things that are sort of counters of time-sensitive event, but also counters of time-sensitive event that adapts to the task or the contextual changes in the organism's environment. Another really cool paper, for any of you who've done trace conditioning in machines, I know many of you have, I certainly have. Our prosthetic experiments wouldn't work without us building trace conditioning into our machines. You'll know that sometimes the natural thing for you to do is say, oh, well, there's a stimulus in the environment. My machine is perceiving something. I might just synthetically create another sort of decaying trace of that stimulus and then give that as extra input to my machine. There's now some evidence in the rat brain that there are these ramping cells that do almost that might either increase or decrease in cell population firing after an event or a change in a situation. In this case, like a rat's running out of maze and sees different colors walls. And there are actually traces, populations that start to gradually decrease or increase their firing rates in response to the time since the task began or the time since salient stimulus, like going from a white wall to a black wall. What I found really cool, and this is a very new paper, it's on bioRxiv, but it's based on a template. It looks like it's been submitted somewhere fancy, work by researchers that in fact we have good reason to trust, showing that you can also find time cells and ramping cells in the human brain. They did a study with 27 epilepsy patients in episodic memory tasks, showing that they could also see similar kinds of time cell activation in the human mind. And not just in something like the hippocampus, there's people who've reported time cells found in the striatum, in the hippocampus, entorhinal cortex, and in our good friend, for those of us who do genital value functions, in the cerebellum. So I'm going to step towards a great book. If you haven't read it, there's a book called Your Brain is a Time Machine by Dean Buonamato, a leading neuroscientist on time. And I'm going to paraphrase Buonamato in saying that the animal brain uses these representations of time or these representations of memory in a few ways. And I think some of the crisp ones and some of the ones identified by Buonamato are that the animal brain uses time to do something I think most of us do in our machine learning research, which is remember the past to predict the future. Now, but beyond that, the brain uses time to recognize and generate temporal patterns, the tapping of your foot, the way that we generate speech or process speech. It can also create subjective perceptions of time. And by this, I mean be able to make the flow of time visible to the organism or the decision-making system that is engaged in a stream of experience. And really importantly for, I think, a lot of the work that we're currently doing in the RLAI lab, and a lot of us have been pursuing, is that the brain uses time to project back and forth in that stream of experience, to remember the past in different ways and to simulate the future or plan. So my view, those of you who know me know that I like to break down the problem intelligence into representation, prediction, and control. And Rich keeps egging me on in this, so I'm going to keep doing it. Is that my view is really that time is in fact a thing that we hope our machine should be able to represent and turn into state, whether they're organic machines or synthetic machines. That time is a thing that we may hope to predict. Timing is a thing we hope to control. And in fact, the flow of time or the progress of time is a thing we hope to use in planning and things like meta-learning. Now, there's a few main considerations here that I think are important when we talk about this. we can think about, and the biological literature says there's significant differences between how we might measure the time since an event, something called retrospective time, and prospective time, how we might keep around our forecast of an ongoing event and measure the time of an event that's ongoing. We might also care about objective versus subjective time, how as a learning machine, biological or synthetic, perceives the flow of time, or how some objective timekeeping device is able to keep track of time, objective or subjective time. There's multiple scales as well that we might hope to think about: milliseconds, seconds, minutes, hours, days. The spans that we might talk about when we consider time might be wildly different, and we might hope that our learning machinery is able to handle multiple spans, and further that it's able to rescale or retime its operation to different spans of events and to different temporal patterns. Finally, I think it's really important that we also think about how learning machines are able to entrain or align to temporal patterns. Think about me sitting here and tapping my hand to my other hand. After a while, some of you might start tapping your hand as well. This idea that we align our temporal patterns to other temporal patterns. What I'm not talking about today, I think is important, but not something that I hope to consider, is whether or not there's a time that's only the present, or whether there's a block universe that we move through in space-time. The physics applications and the physics considerations are, so I'm decoupling from today's thinking. And thank you, Fernando. So I'm coming close to the end here, and I wanted to say a few what I think are the desirable agent abilities. So if I'm putting sort of a call to things we might want to work on, or things that I hope we're going to find important to study in terms of especially our learning machines, I think it would be very desirable for an agent to be able to represent the time since an event. As I mentioned, trace conditioning earlier, or even just keeping around a leaky bucket trace of a signal that an agent has perceived. I think it's really important that agents are able to do this in the absence of stimulus from the external world. I think it's also equally important, and many of us who study predictions care a lot about this too, that an agent is able to estimate the time until a future event or a future events. Even just saying how many time steps until I next see a white wall after last seeing a white wall is a very important thing that we might hope our agents to estimate, and many of us formulate in terms of our, say, general value function learning machines. I think we should hope that agents are able to scale and adapt to different event intervals and align themselves to rhythmic events. And finally, I think this is a really hard one. This is a very interesting one as it relates to tool use, is that I hope agents that we build will be able to use and change the environment that they interact with so as to implement measures of interactive time and objective time. So many of you saw all these diagrams on the slides. I was going to have prizes again for anyone who could tell me like which of the which particular invention these came from. This is the water clock from, I think, 300, is it 300 BC or 300 AD? But it's the water thief. And so I think we want to have agents that are able to begin to implement Mr. Harrison's timekeeper, or understand the motion of other bodies in the world as a mechanism for keeping time outside of their own internal processing units. So with this in mind, I'm just going to share some themes and things that I'm working on. I'm working very hard right now and on an ongoing basis to understand prospective and retrospective timing in machine agents. So estimating time since and time until events. I'm also working very hard to study how agents use and build representations of time, how time has flowed and how it will flow, so they can use this during ongoing continual decision-making problems. So that's the main technical content. I did want to say one more thing. I have some suggestions for the present. We are living in interesting and uncommon times. And so on the subject of time, some suggestions, especially I hope to the students, is that when thinking about time, I want you to make sure that you take your time. Right now is a very challenging time. And so I hope that you focus on your personal understanding. Spend time at your own pace to understand things and try to take time. Protect time for yourself. I would say without any doubt that all of you are much more important than any perceived productivity that someone might cast upon you. So protect time for yourself and take care of you. And as like priority zero, please make time to do things that help your physical and mental well-being. Especially right now. We're all working from home. Many of us are disconnected from our usual social structures. So if you have to choose and you're like, I don't know, should I really like go for a walk, or should I do something to keep my hands busy to make myself feel better? Or should I try to really grind to work on the paper? I think that there's no clear answer there, and that you should make a priority of putting a focus on your own physical and mental well-being. So just, I want to say it to everybody. I've said it to my own teams, but I want everyone to hear that. Like, please take time for yourself and take care of yourself right now. It's not important to be productive. It's important to be well. So with that, time's up, and I'm looking forward to any questions.
Thank you so much, Patrick. People can now unmute and ask their questions or post them in the chat.
So there's a lot of different things that we might choose to keep track of, things that we want to know how long it's been or how long to. Do you have any insights into how we choose out of all the possible things we might want to keep track of, what we should keep track of?
I don't know. I was kind of thinking of using your tidbit algorithm, but I mean, other than that, like that's my go-to. This is really tricky because clearly, if you were to think of like Joseph and I, and maybe many others think about the world as a gigantic stream of bits, a flow of bits, then you could say, well, I'm going to keep like a decaying trace of every single bit in my world. That sounds kind of big. And so I don't actually have good insight as to how we might start to say what events are salient. I'm actually not like saliency and attention come into play here. In the biological literature, how does a rat say have a population of cells that fire when it goes from a white wall to a black wall and not like flecks of dust along the white wall? Or are there cell populations that fire? I don't actually know the answer. None of the papers that I've dug through in my recent memory have addressed how the agents actually do that search and selection process for the features. I'm just call it features, the features that they care about and wish to attend to with respect to time since an event or time to an event. If I run an experiment with you, I was like, okay, cool. I'm going to give you a deck of cards. You should play out the cards. And after you play out all the cards in the deck, there might be 52, there might be less, there might be more. I'm going to ask you how long it took for you to dial out those cards. You're going to attend, that's a prospective timing act. You're going to attend to certain features to help you be able to do that. Maybe you have a stopwatch and you're cheating. Maybe you're tapping your foot. Like maybe your brain is just going to, you're going to try and estimate just based on internal signals. But I mean, I've just cued you as to a kind of question, and I've given you certain stimulus. So this is I think an open question. I don't think keeping track of everything scales, but maybe I'm wrong. But I think there is some kind of feature selection problem here that is near and dear to many of our hearts that might help us start to think about this. Does that answer your question, Alex?
Yeah. Do I have a question? May I ask it?
Yes, please, Shava.
Yeah. So it's very tempting to introduce special variables like time. The question is whether you really need to do that or we are falling into a trap if we are treating time in a special way. It's almost like a philosophical question. What do you think?
I read, it was earlier today actually, I saw an interesting rebuttal. It was the introduction to one of the Nature papers on time. And it was Shapiro was writing, essentially said that essentially that time is just memory. That's not how he titled the article. It was pretty close to that. But the idea that, I mean, when I'm saying time, that's why I said maybe at the beginning of the talk, this is close to approximating memory, is that if you're taking especially a subjective agent-facing view, then really we're asking about how its internal state changes as it undergoes a flow of experience, and it remembers bits. So this is less about, I think, like I'm actually less interested in trying to say, let's make sure we put time into a system. But I guess, again, from a bit-based perspective, I am very interested in how a system is able to maintain an internal state that does a good job of keeping around memory when the external world might not be providing it with the correct decision-making fodder to make decisions it needs to make. And conversely, when there's enough information in the world to be able to keep track of the flow of experience at different scales, so the motion of clouds, the beating of a quartz crystal oscillator, the drip of water through a water clock, that an agent is able to make use of that information to make good decisions and to form its predictions. So I don't actually know if time is special. That's, again, why I sort of waffled a little bit at the beginning. You said memory. But I do think that the kinds of information that an agent gets by taking into account more than it's just immediate stimulus. You said it yesterday with like the long history of the agent, making that its state. That's like the context in things like context tree weighting, when you have a series of symbols that are coming in, compression algorithms, keeping around the last symbols to predict the next one. These are maybe the same kind of thing. I think the reason that we might want to ground our language in time is that many of our colleagues in other fields have thought hard about time and have phrased their investigations in terms of time and how things like ramp cells and time cells and retiming cells operate. And so by using that kind of language, we might find ideas in other fields that we wouldn't find otherwise. So maybe that's the a bullet point for this, is not to say you should all build time and watches into your agents, but more to say that our agents have the capabilities that we're seeing in some of the neuroscience literature. And maybe that's not satisfying. I appreciate it if it isn't.
Okay. Yeah, thanks.
I was waiting for Ashley Dalrymple to call me out on something and like, you totally misrepresented what's happening in the hippocampus. But thanks for that. Make me feel bad, Ashley.
No, I don't know. I'm more of a spinal cord person, so feel free to say whatever you want about the brain.
There's a comment in the chat about the example that you gave, so you might want to look at that.
Sorry, I will try my best to get to it. This is the one thing that my fancy setup here doesn't allow, is easy access to the chat window. Mainly because my monitors are not arranged as they usually are. Okay, I'm gonna open the chat window. I'm doing it. All right. What do we got here? This is not a question, but I think a better example of the street light would be sitting in your metal chair when a train is passing and you don't know how long the thing is. Yeah, I did this as a kid. I grew up in the country, and yeah, like exactly. He's like, this train is going on forever, and you actually have no good information as to when this train is in fact going, like the caboose can come, especially if you're in one of those metal boxes with wheels and you're sitting there in a rural intersection waiting for the train, and it's the only way you can get to town. Which maybe, I know Dylan as well, I think grew up in the country, so, and Ashley as well probably remembers this, a few others, but yeah, so this is, but I think this is like, all those examples are in fact relating to that case where there isn't enough information for you to be able to well estimate. It's like the void of stimulus between the conditioned and unconditioned stimulus that you still have to adapt your predictions and expectations, and that means something ideally is changing within the agent. For like an LSTM or a transformer or any of those fancy deep nets that people understand that I don't, there is a notion of history and memory and state that is being used in the current decisions. And so something is changing inside the agent. And your train example is a great one. The stoplight example is another one, where something changing in the agent, I think, what's up for discussion. And I don't know yet what the right answer is for what that something should be. And it might change depending on the agent architecture.
All right, Patrick, it's Per from Norway here. You hear me?
Yep.
Hello. I have a question about the if you've considered the difference between time as a learning driver or as a in driving learning, as opposed to time in the control problem, more as in the prediction or the use of the policy generation.
So I think I'll go back to my sort of view, my maybe very limited view that really everything is sort of about representation, prediction, and control. And going back to that, I think for either prediction problems or control problems as input to policy, I do think that I want some aspect, and this is appreciating Csaba's consideration as well, that like maybe time is the wrong way to phrase it. Some notion of the span that relates events, I think, is very important in, say, forming the input to a control system. I think we want our learning machines to represent the passage of span to and from events. So I think we want to be able to, again, I will say it just exactly as on my slides, estimate the time until events and time since events as part of, say, what they would pass in or as part of the operation of a control policy. Even if this is somehow boiled into a larger network or something that's a little more black box that attempts to generate a control policy from a bunch of stimulus, for a set of stimulus, I think that in some way we're going to absolutely require in many situations to have representational elements that relate to the span between different events. So that's my way of saying yes to pretty much everything you said.
Could you maybe tell us a little about what you've been working on recently regarding agents being able to represent time?
Yeah. So, I mean, the main thing I've been working on is being probably the most diligent I've been since I was a graduate student, and doing a gigantic literature survey and trying to understand what other people understand. And outside of that, I have I think some of you probably know, I presented it at the university a little while back, but been looking at very simple, fairly hacky, and certainly not computationally efficient algorithms for constructing sort of bits that relate to time from the ongoing flow of experience. So mainly this is a lot of me looking at, say, square pulse worlds or linear walks, and then comparing different kinds of traces, counters, decaying traces, other kinds of incremental ways of changing bits, so as to be able to forecast upcoming events over different spans. So it's been a lot of what people would probably consider really boring work with very linear, shallow agents that operate mostly in like square pulse worlds and linear walks. So, but if that excites you, I've been doing quite a bit, and I'll have some stuff to share soon, I hope. But that's been driving a lot of my thinking. I do, hopefully I'll have something cool and constructivist to share with everyone soon, which looks more at some of the things that Alex brought up, which is how do you sort of figure out which event it is that you wish to keep a trace from. And I know many of you have been thinking along these lines as well, so I think there'll be some time to share that with everyone and get feedback, and we can figure out something new together.
Sounds good. Looking forward to it. So we are almost out of time, so maybe one more question. If not this, I guess Patrick can hang around for a little more time, and if you have any more questions, you can ask. The rest of you can join us tomorrow for a talk by Martha. And yeah, thank you so much, Patrick.
Thanks, folks. Thank you for listening.